Alright, I'm going to continue right where I left off in the last video. I'm going to get started on day 2, which I have, again, also already solved. So I'm just going to be writing this from scratch, just kind of from memory of the problem. But if I remember correctly, day 2 is quite a bit easier than day 1, so it should not take as long. So we'll just get right into the problem. So again, not going to really read much of this. But okay, to get information, a bag has been filled with cubes. The elf will reach into the bag, grab a handful of random cubes, show them to you, and put them back in the bag. He'll do this a few times per game. You play several games and record information. Each game is listed with its ID number, like 11 in game 11, followed by a semicolon separated list of subsets of cubes that were revealed from the bag. Like there were 3 reds, 5 greens, and 4 blues. Okay, so this is what our input will look like. We have each game, and then we have these sort of what he pulls out at each time, and then there's a semicolon between them, and then there's all these things, and so on. Okay, in game 1, 3 sets of cubes revealed, and then put back in, so they're always drawn with replacement, but I can tell you this is not a probability-based, not a probability-based problem. It's just a counting problem. So the elf wants you to know if it would be which games would have been possible if the bag only contained 12 red cubes, 13 green cubes, and 14 blue cubes. So you find out all the games where that's possible, where basically the simple check is just that the number of cubes pulled out at any particular time is always less than their respective colors, right? So for example, this game 3, at this point, 20 reds were drawn. And so if that's the case, it could not have happened with this set of cubes in the bag because there's more cubes drawn out than there were red cubes, right? And so we just asked, what are all the games that are possible? And then I believe we just sum the IDs of those games. Okay. And so our hopeful answer that we're going to get is 2162 because I've done it before. But let's go get our puzzle input. Right, of course, like Advent of Code, there's always a much bigger puzzle input, but that's okay. So I paste in our large puzzle input, and then I create a new file for day 2. And I type up the same main that I did last time. So let's get right into writing this. So just like day 1, I'm going to open that file and call it input. I really even open it, I'm just going to get the contents out of it. And that's in inputs day 2. So also like day 1, we kind of want to look at each individual line. So I'm going to do the same trick as before. I'm going to iterate over every line using the split iterator function. And so I can do that, and I can just split on every new line, right? And so this will work. It'll split me at every particular new line. Okay, so now we're looking at each individual line, which is effectively each individual game, and we have to parse out how many red, green, and blues were drawn at each particular time. Okay, so what we really are just going to look at, this was a trick that I realized and a lot of other people realized, so I'll skip to this, but the semicolons here are actually not important at all. It's a little bit counterintuitive, but really what we're looking for is just in total across all of these draws in this game, is there ever, for example, 19 reds where there were too many reds drawn? It doesn't matter per turn because we're always putting them back in. We just want to know if ever in any game there's more cubes drawn than the particular numbers of each cube that we have. Okay, so we are going to have to do a little bit of parsing still. It's not like that makes it super easy, but we just don't really need to care about the semicolon. We can just kind of treat it like a comma. So let's do some parsing. We're going to do some really cheater parsing because it's pretty easy. The first thing I'm going to do is just call string advance with 5. So what this is going to do is it's going to skip game space. It's going to advance the string by 5 characters. So remember that this line is sort of just a reference into this actual input. So this input is like what we actually allocated to get the data back. The line is not a copy of that, it's just a pointer into it. So we can modify the line, we don't really need to care. We're just gonna change like what part of it we're viewing. And so effectively, this is gonna like, it's the equivalent of doing line equals line 5 dot dot line dot length, which is just moving the line string like 5 characters ahead. But it's a little bit cleaner, and it, less mistakes can be made with it. So we're going to move that ahead, and then we need to read out that number, right, for our game ID. So we're going to use the function conv.parseInt, and we're going to pass in a pointer to our line, and actually that's it. There's nothing else that we need. So this is going to give us our game ID. And if we look at parseInt, what it does, what it's actually just an alias to, is this function stir to i64, which is a little bit nicer to look at, or more self-descriptive, but it's not nice to like read, I don't think. So I alias it to parseInt because it's a little bit simpler. But all it is, we're calling this variant of it where we're passing a pointer to our string. All it simply does is it modifies the string and reads off the number that is at the beginning of the string. And also, I guess it optionally removes the white space at the beginning, because that's a little convenient. And it just returns the number that it parsed as an i64, or a 64-bit signed integer. We can optionally change the base, but we don't really need to. We're going to be doing stuff in base 10. So this is going to read off that number and move basically the cursor of our line, or the start of our line, to be this colon that's after every game number. Okay, so now, well, we're going to skip the colon space. Right, we've parsed out our game ID, and now we want to skip the colon space that's after that. Okay, so now we just need to read each of these things, which effectively are just going to be, well, they're going to be read a number, read the color, skip 2 characters. Read the number, read the color, skip 2 characters. So let's look at how we would do that. Well, okay, so first we need to read the number. We're going to do this, I know we're going to do this in some kind of loop, so I'm just going to write it as a while true. I'll figure out what the actual condition and stuff needs to be in a little bit. But I know the first thing I need is I'm going to call it the count, and we're going to need to parse out another integer. All right, we need to read out the integer that's starting with that. Then we'll be a little bit gross here. We'll advance the line by 1 to skip the space. That's after each number. And then we need a way to read the word, right? Because we want to read that word. So I thought I had something called read word, but I think I have since removed it. Oh, actually, no, I don't. Well, I have removed it, but I have a different function that will actually work well for this. Ooh, we actually have another one that could be just as useful. Ooh. Yeah, let's use this one. There's 2 functions. We could either use read alphanum, which is just reading bytes so long as they are alphanumeric characters. We're reading them out of the string. So that would read our thing and then stop at the comma or the semicolon. Or we could do read until any, where we give it our string. We give it how many things we want to skip, which we would just pass 0, because we're not going to skip anything. And then we pass all the characters we're going to read up until. And so that way we can say we want to read up until a comma or a semicolon. Either one we're going to stop at. So I'm going to say color is conv parse, well, not conv. This one actually comes from string because it's a string operation. We're not converting anything, we're just doing an operation on a string. It's going to be read until any, and we're going to pass in our line. We're not going to skip anything, and we're going to read until a comma or until the semicolon. Okay, and then we will string advance the line by 2, and that will consume the comma and the space, or the semicolon and the space. So I'll comment that, skip comma space or semicolon space. And advance is smart enough to not advance past the end of the string. It does like the minimum number of characters. So really what our condition here is just going to be is while the string is not empty. So there's a function called string.empty, which you just pass in a string and it returns, it's really simple, it just returns if the count is 0. I guess also if the data is null, it also will return that it's empty. But once the count hits 0 and we're out of characters in the string, we'll finish parsing. So that should work for reading to the end of the line. And now we've parsed out our game ID and the count and color, and counted number of each color. And so let's just print out that this is working. So I'm going to have it print, I'll do a printf, and I'll just do something that looks kind of like this. I'm going to print out the color, colon, the count. And I'm going to have to run this. Like I said, it's right after running the previous day. I'm going to pipe it to less because there's going to be a lot of things to do, but let's kind of gut check this. So we have 3 blue, 7 green, 10 red. That looks right. 4 green, 4 red. That looks right. 1 green, 1 blue, 5 red. Yeah, that all looks right. So cool. We have successfully parsed the input. We have it in variables that we can do things with. So let's actually solve the problem, right? We just need to know which games always had less than the correct number of things. So I'm going to do this in kind of a not gross way, but it's not maybe the simplest way. I'm going to have a red max. I'm going to do a red max, a green max, and a blue max. And they're all going to be I32s. So when you have declarations that are all the same thing, you can declare them like this. So just saying they're all I32s and they're all being declared. And by default, everything is 0 initialized in Onyx. And that's actually a really good point. Everything in Onyx is always 0 initialized because it prevents a lot of bugs and it just makes... It helps your sanity. Let's just put it that way. So these will be 0 initialized, which is actually perfect for a max kind of variable because it means we don't have to like initialize them. Like a minimum you have to initialize to like a really big value, but max we can just leave it at 0, which is really nice. Okay, so we know the color and the count. So now I'm just going to do something that looks like this. I'm going to switch over the color, which you're allowed to do. So switch, I don't think I've used a switch statement yet. Switch looks kind of like it does in C. It operates a little bit differently because the case statements are actual blocks, so that you can actually declare variables in them, and they implicitly end at the end of their case statement. So the way this would look is I would write something like this. I would say case red, case green, and case blue. All right, so I'm handling each red, green, and blue. And I can switch over strings because strings have an operator overload for equal equal. So I'm not going to get into this too much, but this is how you do operator overloads. You specify the operator and then the function or macro to sort of invoke for it. And because it has equal equals, switches can operate over it. Anything that has an equal equal operator can work with a switch statement. So anyway, that's all I'm going to do. And then these are all going to be really similar, but we're just going to use the math.max function. I cannot type right now, but we just pass in the previous max and then this new count, and that will keep track of our thing. Now, if we remember, parseInt produces a 64-bit number, whereas redmax is a 32-bit number. You know what, just for simplicity, I'll pass a 64. I'll just make these variables 64-bit. There's no reason I have to use 32-bit, so I can just make them 64-bit. And so then I don't have to worry about casting anything. And I'm going to do the exact same thing for these. I'm going to just make red go to blue and red go to green. So now I'm keeping track of the max of each color that we see. And then, well, we just have to look at our problem. So it just says, include the game only if your maximum number of reds is less than or equal to 12, greens are less than or equal to 13, and blues are less than or equal to 14. So let's just do that. If red max is less than or equal to 12, and green max is less than or equal to 13, and blue max is less than or equal to 14. Then we include our game ID in a sum, right? We're doing a sum over the game IDs. So I'll just call it sum, just like before in the last day. I'll add that sum, or I'll add to that sum my game ID. Bear in mind, again, we're having a 64-bit number. So this is a slight annoyance in Onyx that I do want to solve, but because 0 is an integer, it implicitly becomes a 32-bit integer if you don't have external things that force it to be a higher size type. And so it's a little inconvenient because parseInt returned to 64-bit, and so it's a little inconvenient, I agree. But if we just explicitly say this is a 64-bit, we can get around casting anything. And well, now we have the sum, and so I can just print it out. Right, part 1, and we're going to print out that sum. And I honestly forgot what we're hoping for, but that looks right. 2162, 2162. Perfect. So this is the part 1 solution, right? We're using the same kind of looping over each line. We're doing some string manipulation for the parsing, and then we're using a switch to like do this, right? This could be maybe simplified. You could use a hash map or something, and then you don't have to do the switch case. For this simple program, switch is perfectly fine. All right, so the next part is actually, I think, pretty simple if I remember correctly. The elf asks you, what is the fewest number of cubes in each color that could have been in the bag to make the game possible? And so in game 1, you could have played it with 4 reds, 6 blues, and 2 greens. And the reason that you can do that is because that's the maximum of each color that was seen in that particular game. And so we're actually already computing the maximum of each color that we've seen in each game. And so we're already doing that, so that's pretty simple. So what do we have to do? The power of a set of cubes is equal to the number of reds, greens, and blues multiplied together. The power of the minimum set of cubes in game 1 is 48. Okay, so basically just multiplying together each of these things, and then for every game, find the minimum set of cubes that must have been present. Okay, so for this one, I'm actually gonna not rewrite have a variable at the top like I did before, where I can switch between the 2 parts, because I'm actually just gonna do both of them at the same time because they're so simple. So what I'm gonna do is actually, well, this is my check for game 1, and I'm just gonna say my part 2 sum, which I think I forgot to declare, but I'm just gonna add the red max times the green max times the blue max. Right, which I forgot to declare that, so let's go declare that up here. In fact, I can do the same trick I do below with the other things, and I can just declare part 2 sum like this, right? And then they also start at 0, and that's guaranteed. So now I'm summing up the red max, green max, and blue max, which I was calculating from before. And if I print this out, and we run it, get some extra keys there, but 72513, 72513. So perfect. That worked out. So this was a really easy part 2 if you wrote your code like this, where you're computing these maximums, which you kind of already had to do. So yeah, day 2, much simpler, was a very good problem. This felt like it could have been day 1, but nonetheless, it was a good problem. And we learned some interesting stuff about Onyx, right? The switch statements, some of these string functions for parsing. They're not really advanced parsing functions, but little string manipulation things that can be very useful for when you're reading in something like this. So I'm going to get to recording day 3 now, and then I'll hopefully be all caught up. So then day 4 I can record live. That'd be pretty fun. All right, see you in the next one.